Moving coil galvanometer. So what is a galvanometer? You have seen, in the laboratory that this galvanometer, it is used to detect the current in a circuit. All right. So how this galvanometer works? So before that, we shall see at the principle of a galvanometer. So what is the principle of a galvanometer? The principle says like this. It works on the principle that when a loop carrying current is placed in a uniform magnetic field, then the loop experience a torque. Okay. So for that we have seen, just now in the previous video, that whenever a loop carrying current is placed in a uniform magnetic field, so that loop always experience a torque, in which the loop is, it will rotate in that case. Okay. So after this, we shall see now, right, at the construction of this galvanometer. So here I have drawn two figures, right? This is actually the front view, and this is the top view of the galvanometer. So when you look at the galvanometer, you will find these components here. Okay, the first component that makes the galvanometer is a rectangular coil. So we have, a rectangular coil, and this rectangular coil, it is wound in a non-metallic frame. And the axis of this coil, like this is a coil, we have this is the axis, or we call the axle in other words. So this axle, it is pivoted between two points, and these 2 points here, they are called jewel bearings. Okay, so these are the jewel bearings. Okay, and the two ends of the coil, right, it is fitted with a, which we call a hairspring in this case. Okay, so these are the hairspring, which is of a wire of phosphorus bronze. Okay, all right, and this end of the coil, it is also fitted to, to a pointer here, and this pointer, let's say it is, it should be a very light wire, say like aluminum wire, which is a very thin aluminum wire. And this pointer, right, it is usually used to find out the deflections of the, of the coil, because when the coil rotates, then we will know that deflection, right? When we will know that rotation by the deflections of the pointer. Okay, and this pointer, right, it is fitted here, I mean, with a scale, because from the scale, when this pointer comes at 0, it means this coil here, it is parallel to the field, and when the pointer, right, it points at other than 0 position, it means there is a deflections in the in the coil. Okay, and inside this coil, we insert one core which we call soft iron core. Okay, this is soft iron core, which is in the form of a cylinder. And this whole thing, that means this coil here, now it is placed right between, it is placed symmetrically between two pole pieces of a magnet, which we call like a horseshoe magnet. Okay, now this horseshoe magnet, it consists of north pole and south pole. So we know that the magnetic field is always generated from north pole to south pole, and this magnetic field here, it is a radial field. So when I say radial field, it means that, okay, so for that we will come to this top view of the moving coil. When you look from the top of the galvanometer, you will find like this. Now we have, this is a horseshoe magnet, and these are the magnetic fields. Okay, So these magnetic fields, they are always directed towards, the center of the coil. Okay, towards the center of the circuit, I can say. So these are the turns, right? These line here, these stands for the turns of the coil. Okay, and this is a pointer which is fitted, okay, from the coil. Okay, so as to know the deflections of the coil. Okay, now this radial field, it is used here so as to make the plane of the loop always, because at any positions when the coil, right, comes at, let's say, let me show you by using this exercise book. When the coil, let's say it is at this position, the magnetic field will be like this. When the coil is at this position, the magnetic field, right, because there are always magnetic fields which are perpendicular to the plane of the coil. So in any positions of the coil, as it rotates, you will always find that the magnetic field, it is always perpendicular to the plane of the coil. So that is why we are using this radial magnetic field here, so as the plane of the coil will always be perpendicular to the magnetic field. Okay. Okay, so after having understood with the constructions of the moving coil galvanometer, now we shall see at the theory of this galvanometer. Okay, so look here, we have these two terminals. Okay, so these two terminals, they are actually a source of current. So one terminal, it is connected to this point of the spring, and the other terminal, it is connected here. Okay, so when you allow a current, when a current is passing through this galvanometer, to this coil, what happened? Now the coil, it is actually under the actions of magnetic field. A magnetic field, right, is present, and this magnetic field is radial, as I have shown to before. So because of the presence of current in the coil, and the coil at the same time is in the magnetic field, so this coil will experience what? A torque. And for this torque, we write it as NIA d sine theta. Okay, now what is theta? Theta is the angle between I and B. Okay, so you will find here that because due to this radial magnetic field, the angle theta, okay, it is always 90 degree at any positions. If the coil is rotated, suppose if the coil, right, it is at this point, you will find the angle is theta. If at this point, you will find the angle is theta because the magnetic field is radial. Okay, so theta here means 90 degree. I'll write like this. So which means tau is equals to NIA, just be in this way. So this is my, the torque which is experienced by the loop when placed in a magnetic field. Okay, all right. And I'll name this torque as a deflecting torque. So I'll write with a subscript DEF, which means a torque which deflects the coil inside the galvanometer. Okay. Now please note down here that this I, it is the current passing through the coil, and A is the area of this rectangular coil, and B here, it is the uniform magnetic field, N is the number of turns of the coil. Okay. Now, as the coil rotates, suppose it is like this. Suppose initially the coil, right, when there is no current, let's say the coil is facing like this. When the current I pass through the coil, let's say at any instant the coil, right, shifted like this. Before it is in this way, now it shifts that side, it means it makes some angle, isn't it? So that angle, let's say here, it is alpha, which is the angular displacement. Okay, So this is the angular displacement alpha. So this angular displacement alpha, right? I mean, because of the presence of the spring in this coil, now when the coil is rotating in this direction, then there will be a restoring torque, or I can say, a deflect, a restoring force which will try to move back the coil in the original position. So for that, I will say that whenever there is a deflecting torque, there should also be a restoring torque. And this restoring torque, I'll write it as tau res, which means restoring torque. And this restoring torque, it is directly proportional to the angle of rotation. That is, okay, this is the symbol of directly proportional, and this should be directly proportional to alpha. What is alpha? Alpha is the angle of rotation. Okay. Or I can say this restoring torque here is equals to some constant. If you remove this, you'll get some constant, and that constant is k. So I'll write like this. So this is your equation 1, and this is your equation 2. Fine? Okay. What is k? K is a constant of proportionality, and we call it as a torsion constant. Alright. Now, so in equilibrium, what will happen? In equilibrium means this deflecting torque will be equals to the restoring torque. So when the two torques, right, are equal, it means that this coil will not rotate. So that position is known as the equilibrium position, and in this equilibrium positions we have this is the condition. Okay, so which means instead of tau deflect, I'll write NIAB, tau restoring, I'll write K alpha. Okay, so if you find out alpha from here, you will get NIAB upon K. Okay, so now actually all these quantities here, like N, which is the number of turns, I, the current, area of the loop, magnetic field, right? And even K also, they are all constant here. Okay, the only thing which can vary here, I mean, the only variable here is current, because current can be, increase or decrease from the source. So, but the rest like N, A, B upon K, they are constant. So if they are constant, I'll write constant times I. And for this constant, I'll write it as capital G and then times I. Okay, so this is my equation 3. And this G here, it is known as the constant of a galvanometer, or sometimes you call a current reduction factor of the galvanometer. Okay, so this is how a galvanometer works, or which is the theory of a moving coil galvanometer. Okay. Okay, I think I made a mistake here a little bit, so sorry. I will find out I from here, and you'll get I is equals to K alpha upon N A B. Or I can say this current I here, because all these quantities, they are constant, so I can say this I, it is directly proportional to alpha. Okay. Okay, so this is my equation number 3. I is directly proportional to alpha, it means that the deflection produced in the galvanometer depends on the current. If the current passing through the galvanometer is large, then this coil inside the galvanometer will deflect, right, very large. Okay, and if the current passing through the coil is small, then the deflections in the galvanometer also will be small. So that is the meaning of this equation 3. Also, right, I can see here that this I is equals to some constant, and that constant is G times alpha. Okay, where G here stands for these constants, K upon NAB. And this G, it is a constant of proportionality, or sometimes we call it as another name as, a galvanometer constant. Galvanometer constant, or another words for this is known as current reduction factor. Current reduction factor. Okay, all right. So having understood with this theory, now we shall see quickly about some more terms which are related to this moving coil galvanometer. And the first one is figure of merit. So please listen carefully about this figure of merit, because you are going to do this also in the practical. So this figure of merit, it is actually defined as the current which produces a deflection, of one scale division. Okay, so for that I can write G is equals to I upon alpha. Okay, which means the deflection which produce one division. Okay, so when I say one division, mean when the current I is passing through the galvanometer, and that galvanometer, it shows one deflection, that means from here to one scale deflection, that means from 0 to 1 it deflects. So it means that G is equals to I upon alpha. Okay, from here G is equals to I upon alpha, so this is known as figure of merit. So we define it as what? The current which required to produce one scale deflections in the galvanometer. Okay, so therefore we shall see also about the SI unit of this figure of merit. So from here I can say the SI unit of figure of merit is ampere per, because alpha, it is actually the division, right, in the scale, so I'll write ampere per division. So ampere per division is the SI unit of the figure of merit. Okay. After this, the next terms which is associated with this galvanometer is sensitivity of a galvanometer. So when I say sensitivity, it means that when a small current is passing through the galvanometer, then this galvanometer, it shows a very large deflection. So large deflection when small current is passing through the galvanometer, it means that the galvanometer is more sensitive. Okay, it's very sensitive. So there are two types of sensitivity here. One is current sensitivity, and the other is voltage sensitivity. So first, let us see at current sensitivity. So what do we mean by current sensitivity? So current sensitivity is defined as the deflection produced in the galvanometer, right, when the current passes through it. Okay, so which means, okay, I will denote this current sensitivity as IS. So if IS is the current sensitivity, then I will write this as equals to deflection by current. Okay, so when a current I is passing through a galvanometer, then we get a deflections in the galvanometer. Okay, so that is the meaning of current sensitivity. Or you can say Is is equals to, instead of alpha, or instead of I, okay, I will write, because I is equals to K alpha upon NAB, so but here I is down, so this NAB will goes up, and K alpha will come down, so alpha alpha cancel, so this current sensitivity is equals to NAB upon K. Okay, now voltage sensitivity. So what do you mean by voltage sensitivity? So just like for current sensitivity, we define as what? The deflections in the galvanometer when the current is passing through the galvanometer. So for voltage sensitivity, I will see the deflections in the galvanometer when a potential difference is applied across the two ends of the galvanometer. And for that, I will denote, here as Vs, and this Vs is equals to alpha upon V. Or I can see alpha upon, instead of V, I will write IR. From Ohm's law, we know V is equals to IR. Again, the value of I, I'll write like this. So if you substitute here, you will get NAB upon KR. Alright, so this is the voltage sensitivity. Now, looking at these two equations, let me name this as equation 4, this as equation 5. So from equation 4 and equation 5, now I can tell you that this sensitivity, both current and voltage sensitivity, depends upon the number of turns, the area of the loop, the magnetic field, and this torsion constant. Okay, so when the number of turns in the loop is more, the sensitivity will be more. When the area of the loop is large, sensitivity will be more. When the magnetic field, right, which is produced by a horseshoe magnet is large, then the sensitivity also is large. And when the torsion constant is small, the sensitivity is small. Okay. And for voltage sensitivity, we see just one extra factor, that is upon the resistance. The resistance of that, of the winding. Okay. So when the resistance of the winding is large, the voltage sensitivity, okay, will be small. And when the resistance of the winding is small, the voltage sensitivity will be large. So these are all about the moving coil galvanometer. And after this, in the next video, we shall see about the applications of moving coil galvanometer or the uses of a galvanometer.